Welcome to Tech Talks, a production of the Emerging and Innovative Technologies Committee in the Environmental and Water Resources Institute, EWRI. The objective of the committee is to identify technologies that have the potential to affect fundamental changes in environmental and water resources science, engineering, and management. In this series, we've invited 3 guest speakers to share their projects with a brief presentation, followed by a conversation with our committee leadership. Myself, Dr. Marcus Aguilar of the City of Roanoke's Stormwater Utility, Professor Sierra Young of North Carolina State University, and Mr. Marcus Quigley, CEO of EcoLucid. In session 1, we'll hear about Mr. Adam Erispaha's use of artificial neural networks to improve urban watershed modeling. Session 2 will continue the conversation with Mr. Matthew Garcia's implementation of machine learning to create a next-generation flood alert system. Finally, we'll learn about assessing the risk of lead contamination in private drinking water wells using citizen science data and predictive models from Mr. Mohammed Ali Aksar Fatsahi. I hope that you enjoyed the Tech Talks as much as we did. Please feel free to recommend ideas for future Tech Talks in the comments.
So welcome everyone. This is the EWRI, Emerging and Innovative Technologies Committee, Tech Talks. And we're really lucky to have a few great speakers from Xylem today, Adam and Bryan. But before we jump into that, I'll give a little bit of background. What we're doing is we've invited a number of folks to give quick lightning talks, presentations followed by some questions on one of the more exciting subjects in water resources engineering. And so we have these folks speaking here today, and I'll let Marcus Aguilar and Sierra Young introduce themselves as well.
Hey guys, I'm Marcus Aguilar. I'm the chair of the committee this year. I am a stormwater research engineer at a mid-sized stormwater utility in Southwest Virginia. Excited to hear what you guys have to say today.
Hi everyone, Sierra Young. I'm the vice chair of our committee and an assistant professor at NC State, focusing on robotics and automated technologies for environmental sensing, and looking forward to your talk.
Excellent. So Adam and Bryan, we'll have you share your screen here, and we're looking forward to hearing what you've been up to.
Cool. All right. So just maybe I'll introduce myself, and Bryan, you can follow. Yeah, my name is Adam Erispaha. I'm a hydroinformatics engineer with Xylem, and my focus over the past few years has been finding ways to improve our watershed modeling, improve our hydrologic modeling with machine learning and data science. Yeah, it's been super exciting, and it's been some of the maybe most interesting things I've probably gotten to work on ever. So excited to talk about it today.
And I'm Bryan McDonnell, Senior Manager of Hydroinformatics and Process Control. Been working with Xylem, well, previously MNet, but now Xylem for about 5 years. And basically, we'll work with our clients to come up with innovative solutions to meet their water quality goals and collection system management goals. So also happy to be here.
Cool. Okay, so today we're going to talk about our artificial neural network applications and how we use them to do some watershed modeling. So just a quick overview. We're going to talk a bit about why we would even want to do this. And I'm going to go over some of the architecture, the different architectures that we're using. And then we'll go through some examples and look at some cool plots. So, so why do we want to do this? I mean, I think as you're all probably aware, hydraulic modeling is not an easy thing. There's a lot of there's a lot of parameters, there's a lot of things that make it quite challenging. It's one of the reasons that I was interested in hydraulic modeling to begin with, but nevertheless, it's a really challenging problem, and it's kind of intuitive. All of the different mechanisms that you can think of when a drop of water lands on the earth from the sky, and all the interactions that happen from that point forward are really complicated and very, very interesting. But to try to create a mechanistic model of an entire watershed would be, of course, quite an endeavor. And our approaches to modeling that in a more practical way, while they work well, there's some limitations, and some of these limitations we can kind of get around or improve on with using an artificial neural network. So as far as thinking about the parameterization of these more traditional models, we have kind of a lot of flexibility with respect to spatial resolution, time resolution, and things like that. But it becomes a kind of a practical limit to try to specifically parameterize every little nook and cranny of the water cycle, for example. The reason, one of the reasons that's using a kind of data model or a machine learning model, like a artificial neural network, why it's super interesting for this type of application is that we can kind of learn learn about the dynamics of the system by looking directly at the data and trying to build a model to replicate the dynamics of the system. And it allows us to explore kind of the sensitivity of different parameters and how they impact performance of a prediction. For example, if we want to include parameters like relative humidity over time, or anything else we can think of, cloud coverage potentially, we can experiment with that, and so long as we have kind of a data stream for it. And then kind of further why artificial neural networks, because we have such an kind of explosion in data creation and kind of sources of data, it kind of opens up the possibilities to incorporating a lot of interesting parameters into a model. Another kind of practical reason that these are super useful is that they are super duper fast. Once they're trained, once these artificial neural networks are trained, they can generate a prediction really quickly. Whereas a swim model, for example, it takes some time to run through a simulation and kind of process the results. This is super useful for us, in particular when doing real-time decision support, something that we focus a lot on for our clients. So it's super important for us to be able to take data that's just become available, like what the existing state of the system is, for example, what the water level in a certain tank is, how much water fell in the past 5 minutes from the sky, and then generate a prediction of what the future is going to look like given that information, and then repeat again 5 minutes later. So having to kind of iterate so quickly and update things in real time makes for artificial neural networks. Yeah, and then additionally, I mean, there's with respect to building these models and training these models, being able to rent a supercomputer is really kind of easy these days, which is very cool. So when we want to actually train these things, we can kind of deploy the training process to something super duper powerful for a few hours and then shut the machine off. And yeah, and then kind of more of a philosophical thing. The models that we are building, these artificial neural networks are essentially doing the whole process is essentially doing the process of calibration. Kind of if you think about calibration in a kind of traditional hydraulic modeling sense. From each of these models kind of inception, they're being adjusted to match actual data that's being observed. Yeah. Okay, so let's talk a little bit about one of the architectures that we use for sewer flow prediction. Okay, so we are using a lot of different flavors of artificial neural networks. In particular, we're using a kind of hybrid of a recurrent neural network and a feed-forward neural network. And we use kind of an adaptation of this NARCS neural network, which is stands for nonlinear autoregressive with exogenous inputs, which is just a fancy way of saying it's autoregressive, and we also have other input features other than just recurring predictions around as subsequent inputs. So specifically, what we're using as inputs to this type of model, it varies from application to application, but very typically we're using precipitation time series. So we kind of orient data such that we have some amount of history of rainfall, maybe a couple of days worth, maybe a few hours worth, depending on the application. And we'll use historic flow data as an input. And also super interestingly, we'll use kind of seasonality in order to kind of replicate like diurnal patterns that we see in urban watersheds. And the way that we got that to work was quite easy. It was just really amazing to see it work. So to incorporate this seasonality, we basically just tell the model what time each of the target values exists at. So if we have a time series of flow data, we just also pass on this information that this flow rate occurred at noon. This flow rate occurred at on a Saturday and at 4 a.m. and so on. And just providing that information alone, the model is able to learn about the kind of diurnal patterns of the particular site that we're trying to make predictions on. Yeah, and then what we're trying to predict, again, the label or the target of these particular types of models is flow in a sewer, usually in a kind of a urban watershed. Some details about the types of training that happens. There's lots and lots of options for training these models. In our case, just at a high level, we're using kind of a sequence of training algorithms where we apply an open loop training algorithm, or you can think of it as like a ground truthing training algorithm, followed by a closed loop training algorithm. And the difference is, like, I think of it as the kind of the first batch of training is kind of with training wheels on, and then the subsequent training is more challenging for the model. And the difference is in the open loop training, we are basically passing in previous flow predictions, actual previous flow predictions as inputs to the model. And just tasking the model with making a prediction for the subsequent time step. The closed loop training process that comes after that is actually populating these previous flow predictions with with previous predictions that actually have come out of the model. So in this kind of simplified graphic here, that closed loop concept is kind of visualized by these blue arrows here, where we're passing back in each prediction as input for the subsequent prediction. And then the green inputs here are just any exogenous input, typically rainfall, for example. Okay, so let's look at a few example results here. So okay, this is a hydrograph showing flow in a particular part of an urban watershed that we were working in. And here I'm actually going to compare it to a compare predictions that come from a traditional model to kind of get a sense of the difference here. So this green line here is predictions of the hydrograph from a traditional model, and then the orange line is predictions that are coming out of our artificial neural network for this particular site. Another way of looking at the comparison of these results, this plot over here is showing observations of peak flow for a whole sample set of events, and along the x-axis is the observed flow, and the y-axis are the predicted flows. And the blue dots here are predictions from the artificial neural network model at this particular site, and the green ones are from a traditional model. In this case, this artificial neural network is able to kind of tighten the bands there. Okay. Yeah, and so keeping in mind that this artificial neural network model takes maybe 2 seconds or so to generate forecasts of these predictions, whereas with a traditional model we're usually waiting minutes at least. So super useful, important for real-time applications. Okay, so next architecture that we're going to talk about is one of the ways that we do level predictions. So we apply these when trying to make forecast of river stage elevation, and we've also used them in predicting the water level in large storage assets, in particular for particular clients. Okay, so as far as the architecture here, we're again kind of blending a recurrent algorithms with also simple feed forward algorithm. And as far as what input features we're using into the model, again, we have tons of flexibility, but some of the common and sort of interesting ones are, again, the sequence of precipitation. Obviously, rain is really important for predicting what happens in rivers and such. So we use precipitation sequences. We use historic flow values if they're available. If there's if we have sensors in the watershed, or if there are USGS stream gauges that we have available, that we have data in real time, we can use that as an input. If there is pumping, if there are pump stations that are relevant to the particular site that we're going to forecast, we use that as an input. And we also have had success kind of using kind of derived signals, like passing in the rate of change of level in a river or in a storage asset. So basically, like, how quickly is the level changing, and is it positive or is it negative? Turns out that that's really informative for a model to make predictions about what's going to happen next. Also, we're using adjacent signals. So, for example, if there are stream gauges are river USGS stream gauge sensors like upstream of the particular site or downstream even, or in kind of a more constructed environment if there are adjacent sensors. If there's some pump station downstream that might be relevant, we will use those as inputs as well. And then importantly, that one of the differences with this particular architecture is that we're asking of the model to return a sequence of values, and the sequence being a forecast, and however many elements there are in the sequence is just a function of how long we want to try to stretch out the forecast. So let's some examples here. So this is a plot showing a 2-hour forecast along a number of test samples. And these are samples that are, these are events rather that were not used in training. So it's, basically validation events, I think is the jargon that we use. So the green line is the observed level. In this case, it's a storage asset in a particular city that we're working in. The level over time in this particular assets, and then the blue line is this model's prediction of what the level is going to be, 2 hours into the future, and it's time shifted so that they're these signals match up. And this is super impressive, really nice fit. This was just amazing to see. In this case, I mean, we were working really hard to improve our predictions for this particular application, and we were blending traditional models with neural networks, and just as we progressed, we kind of kept paring down the traditional model more and more to simplify things and remove kind of unknowns, and then ultimately just ended up completely removing the swim model that we were using, and just entirely relying on a neural network to do these predictions. And it turned out to be really effective, really fast. And so that was really exciting. And it almost makes you a little sad for, I really do like swim, but it's just, these results are just really amazing. So it's hard to not decide to go with this. So okay, same time series, just zooming in here. And again, these are this validation events, so it's stuff that the model hasn't seen. So this is an animation showing how this model kind of learned over the progression of the training process. The first frame here is very, it's way off course. It's just like basically randomly initialized. The guts of the neural network just randomly initialized, and then really quickly it infers and learns about the kind of the dynamics of this particular system. So okay, the last graphic I think I want to show here. This is we're trying to come up with a name for this type of plots. I think we're using noodle plots, or maybe like a fur plot or something. I think these are cool. I think these are it's also I think a little bit more of a useful way of looking at the kind of the quality of the predictions that we're getting. So this is results coming from the same model that we were just talking about. This is predicting water level in a storage asset. And then the green line here is a standard time series of observed data in the storage asset. And each of the little blue pieces of fur, noodle, or whatever you want to call it, is an individual forecast. You think about, when we're doing this in real time, obviously we don't know what the future is going to hold, and we only really have information about everything. And when we're going to, use the results from these models in practice. The thing that it doesn't really matter as much like how accurate all of our 2-hour predictions are compared to all of the future 2-hour observations. It matters much more looking at the whole kind of sequence of a forecast to kind of make decisions in real time on the fly. Yeah, and so each one of these little noodles is a in this case, I think they are 12-hour forecasts. So we see that in the beginning of each of these lines, the fit is tighter, which makes sense. It's easier to predict the nearer term than further in the future. But I mean, we can see like where it's really important for us to be able to predict when level is going to rise. It's really important when water is rising, for example. So even in kind of this period of time, like our forecasts are correctly predicting that the water level is going to go down, but eventually and gradually the further term, further into the future parts of each of these forecasts is predicting kind of this upswing, and then we kind of start predicting along the rise of the rising limb here, and in some cases it's a lot tighter than others. In some cases like this guy right here, I think because I think there happened to have been a really steep slope between just two data points, and that's that rate of change piece of inputs was particularly sensitive, I think, for this particular forecast here. But I mean, overall, it's really cool to see all of these forecasts and them kind of predicting the trend. And in some cases, doing a really nice job of it pretty far into the future. Like these ones here, I mean, the whole forecast sequence is really pretty tight. But yeah, hopefully I didn't go over time, but I think I was going to stop there and open up for any questions.
Yeah, no, this is great, Adam, and thanks for doing the presentation. And it's really interesting stuff. I think everyone is excited to see where machine learning in particular is fitting into hydrology. And so this is great. It's a great intro to everybody. I'll start out with the first question here and then open it up to Marcus and Sierra as well. One of the big questions that comes up frequently around machine learning based models or other forms of artificial intelligence, and particularly in something like forecast prediction for what might be significant threats to life or property, is the ability to explain exactly what's happening with the model. So the model is wrong. It's frequently wrong, and as all models are, right? And occasionally bad things happen in flood engineering in particular and water resources in general. It's not a question of if it's going to happen, it's just when you get kind of conditions that deviate from what's expected. So my fundamental question is, how does this all play out, particularly in a legal context or even from a client perspective, around explaining what the model is doing, particularly when you're throwing in like time of day. We don't know why time of day is important, but it reproduces the diurnal curve really well. Or we picked these adjacent signals. They're not in the stream that we're actually modeling, but the model says they're pretty good predictors. Or you even threw in kind of wild variables about humidity and cloud cover and things that we know from a mechanistic perspective are not directly correlated with the things that we're trying to observe. And yet, if they're good predictors, they'll be used by the model anyway. And in fact, we could probably come up with predictors like in a legal case that make no sense at all, right? But would predict the results very effectively. Yeah. So yeah, I'd love to hear your thoughts on this and then like how clients have felt about that. I know it's a complex question, but I think it's one of the most important. Yeah, thanks, Adam.
Yeah, definitely. So a few things to touch on that. So one of the ways that we try to one of the ways that we make sure that we're confident in the predictions that are coming out of these models is by creating kind of a set of models that are trained with the same data, but initially kind of like perturbed in different ways, initialized slightly differently, and we compare the predictions from this set of models that are trying to target the same phenomena, and we measure the deviation in all of those predictions, and we infer that in places where the deviation is very small, we have more confidence that the system that we've modeled, that the inputs and the kind of architecture decisions we've made are stable, and kind of more that we can kind of rely on them more. And on the flip side, in cases where these models deviate a lot, we would make the conclusion that we really don't have confidence in this in making a prediction with given the input state, for example. So that's one way that we make sure that we are confident in making decisions with these models. Another thing is to your point about what's actually going on inside the models. Totally I get empathize with that. When I was first working on this project, working on implementing these algorithms. Yeah, I mean, I had like nostalgia, and I was like a little slightly like, I had nostalgia for like grad school hydrology and like all of the interesting parameters, and when you're using a traditional model, like you can point to exactly this or that lever that you're changing, but what the fear is that you're kind of like losing a connection with those parameters, and how they influence the system. But the way that we deal with that is by through sensitivity analyses, basically. So we'll generate a spread of curves where we're holding everything constant in a system except changing one of the input parameters to the model, and then we can see okay, when we increase, for example, the amount of rainfall, holding everything else constant, the water level changes in this or that way, or increases, and actually in that way we can use the same principle for actually learning about more the influence of like more like exotic input parameters potentially. Like if we wanted to understand, okay, how much does, say, the like relative humidity over the average relative humidity over the past month, how much does that matter for the flow rates given some storm in the future? We can train a model with that, using that information, and then run a sensitivity analysis and see like did we learn that like relative humidity even matters? And it probably doesn't matter nearly as much as rainfall, of course. But
do you
we can see
in setting the models up, do you make decisions about what's appropriate or not, or do you kind of trust the model? I mean, that's one. So like let's say you did find that a parameter that is kind of uncomfortable as a hydrologist, as a predictor for something is fairly straightforward mechanistically. Would you also feel comfortable as a scientist excluding that variable because of that intuition? And what are you not including in the first place that is wholly reliant on your opinion as an expert? Is that comfortable? You're not gonna pick something that makes absolutely no sense for predicting hydrology, but then how many shades of gray are there between there and knowing that rainfall predicts runoff? I mean, there's a lot of and you don't have to answer it. It might be rhetorical even, but yeah. Let me open it up. Let me open it up to Sierra first, and see if there's another question from the committee. Yeah.
Sure. So great talk, by the way. Thank you very much. I had just had a question, or if you could just comment on all of the training data that goes into these models, because when you kind of embark on the journey, collecting all of that, decision making, understanding how much data is enough to adequately train the models, for someone who might be interested in getting started on this kind of approach, maybe if you could discuss or comment on kind of your approach to curating those data sets.
Mm-hmm. Yeah, it's definitely, it's quite a challenge to answer a question like, is this model good, for example, or is this model better than that model? Because, and one of the reasons that is often a challenge is because of what data is available and how we've used it and how we split it up into training and testing and so on. For example, we can build an excellent model to replicate some event. If the training event, the training data is like almost exactly the same. If we were lucky, well, maybe unlucky. If we were unlucky in a situation where we train a model with rainfall data and validate it with other events. If it just happened to be the case that the validation events was extremely similar to the training events, and that sample set of data that we trained with was like an anomaly, to what actually happens in the system. Then we're kind of in trouble. So it's a matter of I mean, first of all, we want to use as much data as possible. It's always better to have more data, but there's a lot of kind of techniques, I think, that we go through to make sure that that we have as much of like the classes of events and kind of states of the system replicated in the data set. So a couple examples. One technique is to kind of cluster the training events into similar categories. So if we have a set of rainfall events, for example, and 50 of them are really, really similar, and then there's like 3 big ones that are quite different. We go through a process of clustering to kind of balance data set. So the model spend 50 times as much energy learning about these small, very similar events that aren't as important, and spending not enough time on the larger events. So in that way, we'd actually either omit a lot of those smaller events or come up with like kind of a hybrid class that represents that type of event. Yeah, so that's one way to kind of try to make sure that the model is generalizing properly. Another challenge that we've worked a lot to overcome is dealing with the relative importance of like dry weather conditions, for example, to like the peak of a rainfall event. Like if you look at a typical urban watershed hydrograph, most of the data is just like little diagonal patterns over and over again, and then maybe depending on where you are, there's 15 really large events or 2 really large events over a year or something. But those few really large events are really what we care the most about. So one approach that we use is to kind of do some type of weighting to penalize the model more for missing on those really large important events and being more relaxed on the error for like dry weather patterns.
Yeah, that's really interesting. And Marcus, just to kind of round out the discussion on the question around, what are your thoughts? Questions for Adam and Bryan?
Yeah, so a couple of just comments, I think. First, I thought it was really interesting how You talked about initially used both a swim model and the ANN, and then over time, out the swim model, you slowly kind of just stopped using it, which also gives me a bit of nostalgia, being kind of a modeler. So I think that's pretty interesting. I've read a good number of papers that mix the two things together and try to find some mixture of, you know, the mechanistic model and the black box model. So anyway, I just thought that was a really interesting presentation. Another observation that I think, you know, Marcus touched on this, but I think it's just really an important conversation in operational hydrology is, you know, there's these guys that talk about the model having to work for the right reason. I think it was James Kirshner, I think he's at Berkeley, wrote this paper about that 2000 something. And anyway, it's like we're doing something that's really far from that, right? We don't necessarily know why the model's working. We've moved away from process here, which isn't necessarily a bad thing. We're leveraging the technologies that are at hand. But I think there are a lot of hydrologists and scientists that would say, like, why are we okay doing this? You know, why is it okay for us to essentially process the signal and forget about sort of the processes that are underneath the hood? So that was the second, just a comment, and I'd like for you guys to talk about that a little bit. The last thing I'm going to ask is a question. I'm thinking of lag time in urban watersheds. So the fastest lag that we have is probably on the order of 5 to maybe 15 minutes between the rainfall peak and when we see the flood response on the ground. So we've got some pretty heavily instrumented basins and catchments. So we're talking about moving from a swim model that operates on like the minutes to hours, you know, runtime, to an ANN that's like on the seconds. I understand that that's faster, but I guess my question is, does that faster really matter from an operational perspective? Does that question make sense, Adam?
Yeah, I think so. Yeah. Yeah, so let me address the first part of the question, if I can. Right, so yeah, I have, I'd offer maybe I don't know if philosophical response potentially, but you know, a lot of models that we use are empirical models that are derived from looking at data and, you know, coefficients, runoff coefficients, and so on. It's a lot of these models are derived from looking at data, and really, I really think that a machine learning model, or at least artificial neural networks like the ones that we've talked about today, they're really, you can kind of compare them to an empirical model, like that we might use, like the rational method or whatever, something like that. You know, the difference is that we have way more data available to us. We don't have to do the math ourselves, you know, on pencil and paper, and we can iterate and try, and we can basically build you know, empirical models that are highly localized, that are for this particular manhole in a, you know, in a such and such a urban watershed, so you know, in that way, I think that this isn't necessarily like a complete departure from traditional modeling. Yes, it isn't mechanistic, but it's akin to a lot of like empirical models, I feel. The second question is regarding timing. Yeah, so you know, maybe Bryan, you can also maybe comment on this, but if you want. But
sure.
I definitely, it definitely is quite important. Maybe the example to maybe illustrate this is we with an ANN we can run like 500 iterations in less than a minute or something like that. It was, I forget how we benchmarked it, but it allows us to expand how much kind of solving we're doing when we're trying to optimize for a control strategy. So we can try a lot of different things and kind of pass them along to a model.
Is that like inputs? Is that like having, you said 5-minute rainfall? Do you also put in 5-minute, 7-minute, 10-minute, 15-minute, 25-minute? Just like, do you just put a whole bunch of predictors in like that and then see how it comes out? Well, for addressing the lag issue. Do you create a bunch of kind of synthetic predictive variables on the input side? Is that how you deal with it?
One approach that we take with inputting rainfall is to pass in as an input a sequence of rainfall history. We've experimented with like how much of a sequence of rainfall history we should use, and I found that it depends, but which actually makes sense based on the lag time of a watershed. But by passing in a sequence of rainfall history, the model is then tasked with figuring out if there was this amount of rainfall that occurred 12 hours ago, how important that is that into my prediction for the next time step.
Yeah. Does that answer it, Marcus?
Yeah, that's good. I'm kind of thinking more about just when we're let's say we're responding to the model's output. So for example, a flood model that you're using your ANN to predict a flood wave in an urban district. So your the speed that you can provide results using these models is really fast. But the speed that a traditional swim model could do it, even if you were running it in real time, it's a little slower, right? It's not going to be able to run in the 2-second time frame. Maybe it'll take a couple of minutes or something like that. But I guess what I'm trying to get at is you're providing data faster. You're giving these faster output responses. But on the user side, does that marginal improvement help? Does it mean that I can, as a utility person, I can go out in the field and do something? I can shut the road down. I can evacuate the house. I can do something in the wastewater system. Does that make sense? Does that gain in speed really help me from an operations standpoint?
Adam, do you mind and support a little bit? That is a fantastic question, right? So response time and any sort of controls recommendation. So typically, there's all sorts of levels of how the machine learning has augmented what's happening to predict what's happening in the collection system. And you called it out very clearly. There's an approach where we augment, for example, a swim model with replacing the hydrologic response with CRIS. And then there's on the other side of that where we look at actually predicting levels in the system. So, and then there is a blend therein where we do our best to retain a number of the conveyance assets so that we can actually simulate and understand the hydraulic situations therein. And so while data latency is normally a major discussion point, and it's a whole presentation on its own. So if we can get a prediction of an adverse hydraulic condition out maybe 2 hours ahead of time, you're already probably 15 minutes late. Worst case scenario, if you're on 5-minute samples and then your data upload every 5 minutes, so you're probably about 15 minutes late. The actual appreciated kind of prediction horizon, it really depends on the client and it depends on their system. And it really depends on what operation options that they actually have, right? But what tends to happen is we can feed this into a decision support dashboard, and maybe the operations team will have remote control of certain assets. If we can do longer term predictions, like, you know, we've got some clients that have super flashy systems. So, I mean, getting that information as soon as possible is great. We have some clients with like not as flashy systems, more like sanitary systems. And then these systems, we can, you know, provide a longer term recommendation to how to manage those flows. But, you know, it really is one of the other things that we can do is we can actually serve these prediction data, these, you know, predictions of the hydraulic system to an automated controller. So the controller then would actually then start, you know, learning and specifying how to move the gates and where to put them in real time. You know, one of the strategies that has been like really good for actually doing like watershed management and doing a control strategy is a market-based optimization strategy that actually serves to request when certain assets are under stress, and these assets are communicating among each other, and they can request other assets will step up and help out. And that system is served really well with any form of prediction, so that I can know when I can predict like a peak depth coming in about 30 or 40 minutes, I can ask my other neighboring storage assets to start diverting flow to dampen that peak flow.
Yeah, this is great, and I appreciate this is a lot of time you guys have given us this afternoon, and a great presentation. It makes me think the committee should set up maybe a roundtable discussion specifically on this subject, because I know I could go another couple of hours, frankly, and not get bored at all. Great talk, and thank you so much, and take care. Stay safe. Thank you.
Thank you.
Yeah.
Take care.